Let us discuss about the second property, case 2, for finding the inverse Laplace transform, where ds or denominator of the function has complex roots or imaginary roots. So if the excess is given by this equation, suppose for the first example, ds will be the denominator s square plus 4s plus 23. So if we break this signal function s square plus 4s plus 23 like this, s square plus 4s plus 4, then you can subtract 23 minus 4 like this. So you will get this s plus 2 whole square plus here 23 minus 4 19. So this becomes s plus 2 whole square plus 19 root over 19 whole square. So this becomes your complex root or imaginary root, because you can see here that s plus 2 plus root over 19 square, you can write it like s plus 2 whole square minus I root 19 whole square. So I square minus I square becomes plus 1, so that this plus symbol you can substitute by minus I. Okay, so this square can be converted into two factors like s plus 2 plus root over I root over 19, then s plus 2 minus I root over 19. So if you put this denominator ds equal to 0, you will get this equal to 0 and this equal to 0, which produces this two value of s is equal to minus 2 minus I root 19, s is equal to minus 2 plus I root 19. So these two solutions are complex solution or imaginary solutions. So this type of, when presence of this type of root is there, then we have to make this function, we have to convert into a form where we can use the formula of Laplace transform of sine signal or cos signal. Suppose for this type of signal where in the numerator there is a constant, we can use the Laplace transform of sinusoidal signal. Suppose this formula Laplace transform of sine omega naught t ut is given by omega naught square by s square plus omega naught square. So omega naught is the frequency component of this signal, so this is a constant value. So here it will be constant and here will also be a constant square value, so this is ultimately a constant. So if you compare this given signal here, so we have obtained this denominator like this. So if we put this denominator here like this, so we can make this function look like this. So this is omega naught square, suppose, so omega naught will be root over 19. So if you put root over 19 here, you have to divide this value in the denominator so that this 2 will cancel out, and there was a 2 from in this earlier in the given function, so that will be here. So this 2 by root over 19 if you take outside, and this format will be similar to like this equation number 2 right hand side. Okay, so you can see that there is a shift value here, and then s plus 2 is there, so you cannot use this basic formula. You have to use this frequency shifted version of the sinusoidal signal. So s plus a of v square, for the frequency shift we have to multiply here e to the power minus 80. So this is also a formula of sinusoidal signal, shifted sinusoidal signals Fourier transform. Okay, so if you compare now this equation 1 and this equation 2, their right hand side are in the same format. So their omega naught, you can say it is root over 19 and a is equal to 2. So if you take the inverse Laplace transform of this, you will get this. Okay, so that I have written here L inverse equal of this becomes this function. Okay, so if you put the value here omega naught and a value you have put here, then you will get this e to the power minus 2t, a is equal to 2 here, and omega naught is root over 19, so sine root over 19 t ut. Now from this equation, if you take inverse Laplace transform, you will get xt. So xt can be given as L inverse xs. So xs is this one, this constant is there, and this is the s function. So this constant if you take outside here and you take the L inverse in the xs where there is s is present. So if you take the inverse transform of this, you can directly write this equation. You can use and you can write the time domain inversion signal, this signal here. Okay, e to the power minus 2t sine root over 19t ut you can write from here, and this 2 to the power root over 9 2 by root over 19 will be there. So this is the xt value for the given signal xt. So what we have done, if you see, that we have converted this signal into a form where we can get the complex roots. Okay, so when complex roots are present, then you have to find the solution, time domain solution in terms of sine or cos signal. So when there is a numerator constant, then it will be basically a sinusoidal signal, but there is also a shift in the frequency that indicates that you have to use the shifted sinusoidal signal like this. So if you use this formula of Laplace transform, then you can correlate 1 and 2, and you can find omega naught and a value for the given function axis. Okay, so omega naught a if you are getting, then you can find the time domain signal is this. Okay, so you have obtained this. This basically we have done. So this here we have just kept this one constant from there, and the inside function is, when we suppose you have taken inverse Laplace transform of this one, then this constant will not be affected. You have to just take the inverse Laplace transform of this part. Okay, that is what we are doing. We are taking this constant as it is, and we are taking inverse of this function, and inverse of this function here I have written 19, that means root over 19 whole square. So this inverse Laplace transform we have just derived previously. This is given by this sinusoidal signal, shifted sinusoidal signal. So ultimately xt can be given by this.